Hello friends, welcome to this video. In this video, we are going to implement the CBAM, that is Convolutional Block Attention Module in the PyTorch framework. So first of all, let's read the abstract of the paper. So it says, we propose Convolutional Block Attention Module, that is CBAM, a simple yet effective attention module for feed-forward convolutional neural networks. Given an intermediate feature map, that is the input, our module sequentially infers attention map along two dimensions, that is channel and spatial. So if you remember the squeeze and excitation network, it only works with channel wise. And here we have both, that is channel and spatial attention. So let's read the abstract. Then the attention map are multiplied to the input feature map for adaptive feature refinement. Because CBAM is a lightweight and general module, it can be integrated into any CNN architecture seamlessly with negligible overhead and is end-to-end trainable along with base CNN. So you can easily use it in your image classification, object detection, and image segmentation tasks. We validate our CBAM through extensive experiments on ImageNet 1K, MS Coco, and VOC7 datasets. Our experiments shows consistent improvement in classification and detection performance with various models, demonstrating the wide applicability of CBAM. The code and model will be publicly available. So now let's have a look at the block diagram. So here you can see the overview of CBAM. It takes the input feature, pass it through the channel attention module, multiply it with the input. Then this multiplied input act as the input for this spatial attention module, and the output of this spatial attention module again multiply with this input, and we get a refined feature. Now let's have a look at the block diagram for our channel attention module and spatial attention module. So here you can see both the block diagram explained in detail. So these diagram would help us in implementation. So first of all, the input feature map goes into the channel attention module, where it passes through two operations, that is max pool and average. Then both the feature map pass through the shared MLP, that is multi-layer perceptron, and we get two features which we add and pass them through the sigmoid activation function, and we get a channel attention. And this channel attention is multiplied with the input features, and this multiplied features would pass to the spatial attention module. Here it begins with channel refined feature map, passes through two operations, that is max pool and average pool, but along a different dimension. Then these two are concatenated and passed through a cone layer, and the output of this cone layer is passed through a sigmoid activation, from where we get a spatial attention. This spatial attention is then again multiplied with the input, and we get our refined feature map. So this is about the block diagram of both the channel attention module and the spatial attention module. Let us now try to implement them in the PyTorch framework. So first of all, we're going to define our class called channel attention module. After that, we're going to define our initializer. So here we would take ch as one variable which would indicate the number of channel in the input feature map. Second is the ratio. Its default value is 8. So this would help us to decrease the number of feature channels in the shared MLP. So if you see the diagram here, you can see the feature maps are decreased. This is where the ratio would help. Now we need to define two operations here, that is max pool and average pool. So let us define those. So we're going to call average pool and the max pool. So here are these two operations which would help us with these. Next, we're going to build an MLP. We're going to call it self.mlp, then nn.sequential. So inside this, first we're going to define a linear layer. In TensorFlow, it is called dense layer. Okay. So first it would take number of input channel, then number of output channel, and the bias would be false. It is then followed by the ReLU activation function. After a ReLU, we again have the linear layer. So the input for the linear layer would be channel divided by ratio, and the output would be original number of channel, and again bias would be false. Now we're going to define the sigmoid activation function separately. So these are all the layers or functionalities which we require. Now let's define the forward function where the execution would happen. Okay. So first of all, we're going to do the average pool. We're going to pass x here. Then in the x2, we're going to do max pool. Again, we're going to pass the input. So now let us print the shape of both of them. Let's execute them. Now here we need to give the shape to this tensor. So this x represent the feature map. So first of all, it would have a batch size, the number of feature channel, that is 32. Next, the height and width of the feature map. So just imagine as it as a intermediate feature map. Now let's have a variable called module. Copy the name of our module. Give it the input, that is ch 32. Now we're going to say module and the input x. Let's run it. Okay, my mistake. It should be module, not model. Okay, here you can see the shape of both the tensor, and here you can see this 1 and 1 we need to remove from here. We just need 8 by 32 in both. So we can apply a squeeze operation. So here we're going to say squeeze on the last dimension. So let's run it again. So you can see perfect. Again we're going to apply the same, and we're going to get our desired shape. Now after that we can apply the MLP. Input would be x1. Same we're going to do with x2. Let's run it. Now we are going to add both x1 and x2. You see, we add and pass them through the sigmoid. Now this is done. Now we need to multiply these feeds to the input. So if you remember, the shape of input is this: batch size, number of channels, and height and width. And this feeds shape is 8 by 32. So now we need to again add those 1 and 1. So we're going to do the opposite operation. We're going to here apply unsqueeze 2 times. Now we're going to say, let's going to call it refined feature. Refined feeds. X multiplied with feeds. So we are done here. So we have implemented this. Now let's get the output from this module and print it shape. So it should be exactly of same height and weight number of channel as the input. So exactly same. So we have finished with our channel attention module. Let's now work with the spatial attention module. So let us define our class. So inside the class we have this init function which takes one argument, that is kernel size, and its default value is 7. Now we need to define a convolution layer. The convolution layer would take two feature channels as the input and produce one feature channel as the output. The kernel size would be 7, and according to that padding would be 3, and we're going to set bias to false. Now we need to define the sigmoid activation function. Now let's move on to the forward class. Forward function, not class. Now again, in the spatial module also we have two operations, max full and average full, but on different dimension. That is the difference. So we're going to say x1 torch.mean. X as the input, on which the dimension we want mean, that is 1. This. And we're going to say keep dim, that is keep the dimension as it is. Okay. Then x2, another output we do not require. We're going to say torch.max, and same number of same thing. Now let's print both x1 and x2 to check any error. Call this function, the function that run it. Okay, we have this shape, and this is fine. The shape is really fine. Because the error here is because it does not return anything, yet it has this error. We have this feature map. This is basically the mean feature map. This is max. Now let us concatenate both of them. You can call it feeds. Let's give a space. Torch.cat x1 x2 on the dimension 1. Now let's print the feeds just to check its shape. So you can see it has two as the feature channels. That is why in the cone layer we have 2 here. Now let us apply the cone. Then we can apply the sigmoid. Okay, so we have this attention, and we're going to multiply this with the input. So we're going to say defined feeds x into feeds return refined feeds. Let's again check the shape. It should exactly have same shape as the, and also we're going to check for any error. Okay, we are running fine, everything running very smooth. Now we're going to define our CBAM function, not the function, the class or module, and here we're going to say define the initializer, and here we're going to give number of channel because we require them for the channel attention module. CBAM is basically combination of both the channel attention module and spatial attention, but in practical you can also use like any of those individually also. It is not necessary, but we are implementing what the author has mentioned in the paper, so that is why. Now this that statement is really important, otherwise we're gonna have an error. So first of all, we go to the diagram. Here it calls the channel attention module, then spatial attention module. Let's follow that sequence only. Self.ca channel attention module, and forward function, it take the input, and here it is really simple. We're gonna call CA first input, and we output the refined feature map. You see, we multiply them both. So this is done. CBAM class is really simple. Here we're gonna say CBAM. Let's run it. Okay, yeah, my mistake. I'm pretty fast. Does not see things. That's a part of you. Because we always learn from our mistakes. Just make mistake and learn from them. Just don't repeat them in a short period of time. Okay, so we get our exact same shape as the input. So we have successfully implemented the CBAM, that is Convolutional Block Attention Module, in the PyTorch framework. So I hope you enjoyed the content, and if you enjoyed it, then share it, subscribe the channel, and like the video. And if you have any query, just comment it. Thank you. Have a nice day.